Hello all, welcome back to Edimoon Tutorials. Myself Geetika and I am here to help you all with the subject computer organization. So we are in our first chapter, register transfer and micro operations, in which we have discussed about register transfer language, register transfer, bus and memory transfers, and we are in the topic arithmetic micro operations. So as seen in the previous videos, by using the list of arithmetic micro operations, we can implement these following circuits. We have seen the implementations of binary adder subtractor, binary incrementer, and now we have left with the one more implementation, that is arithmetic circuit. So in this video, let us see the implementation of arithmetic circuit in detail. So arithmetic circuit is the most important implementation out of all the four implementations, because the previous implementations we have seen are binary adder subtractor or binary incrementer are used to perform either addition operation or addition subtraction operation or increment operation, whereas arithmetic circuit is used to perform all the 7 arithmetic micro operations. It uses full adders to perform these operations, and multiplexers are also used to provide different inputs to the circuit in order to obtain different arithmetic operations as outputs. So let us consider 4-bit arithmetic circuit as an example. The block diagram of a 4-bit arithmetic circuit is as shown. Here we consider two binary numbers of 4 bits each, say A and B, and the 4 number of full adders. So the full adders has the two inputs x and y, that is x0 and y0 are the inputs of first full adder, x1 and y1 are the inputs of second full adder, x2 and y2 are the inputs of third full adder, and x3 and y3 are the inputs of fourth full adder. So the A bits of register A are given directly to the x inputs of the full adder, that is A0 is connected to the x0, A1 is connected to x1, A2 is connected to x2, and A3 is connected to x3. And the y inputs of the full adders are given using 4x1 multiplexers. 4x1 multiplexers, as we know, take 4 inputs and gives 1 output. So the outputs of 4x1 multiplexers are connected to the y inputs of the full adders. Here we use carry input Cin, which is given as the carry input C0 to the first full adder. So this full adder adds the bits x0, y0, c0 and produces the sum d0 along with the carry c1. This carry is transferred to the next full adder connected. So this full adder adds the bits x1, y1, c1 and produces the sum d1 along with the carry c2. So this c2 is transferred to the next full adder connected. So this full adder adds the bits x2, y2, c2 and produces the sum d2 along with the carry c3. So this c3 is transferred to the next full adder. So this full adder adds the bits x3, y3 and c3 and produces the sum d3 along with the carry c4. So c4 is the carry generated by the last full adder. So this is represented using output carry. As we know, the 4x1 multiplexers has two select inputs S1 and S0. So these two select inputs are connected to all the 4 multiplexers, and the 0 inputs of the 4 multiplexers are given using B bits, that is B0 is connected to the 0 input of first multiplexer, B1 is connected to the 0 input of second multiplexer, B2 is connected to the 0 input of third multiplexer, and B3 is connected to the 0 input of fourth multiplexer. And the 1 inputs of the multiplexers receive the complements of B bit, that is B0 complement is connected to the 1 input of first multiplexer, B1 complement is connected to the 1 input of second multiplexer, B2 complement is connected as the 1 input to the third multiplexer, and B3 complement is connected as the 1 input to the fourth multiplexer. Here these complements are obtained by implementing a NOT gate. NOT gate is used to complement the inputs. And the 2 inputs of the multiplexers are given using logic 0. So logic 0 is connected to all the 2 inputs of the multiplexers, and 3 inputs of the multiplexers are given using logic 1. Here logic 1 is obtained by implementing a NOT gate, by complementing the 0 by implementing a NOT gate. So the logic 1 is connected to all the 3 inputs of the multiplexer. Here the bits D0 to D3 represent the resultant output sum. So this is all about the construction of a 4-bit arithmetic circuit. Now let us see the functionality of a 4-bit arithmetic circuit. The functionality of a 4-bit arithmetic circuit is completely based on the two selection inputs S1 and S0 and also the carry input Cin. So by controlling the value of y with the two selection inputs S1 and S0 and making Cin equal to 0 or 1, it is possible to generate the 7 arithmetic micro operations. This can be shown using a function table. So here we have two select inputs S1 and S0 and also a carry input Cin. These 3 binary variables have the 8 possible outcomes, that is 000 to 111. And we have input variable y and also output variable d is equal to a plus y plus c. This is obtained by the full ladder. That is, the full ladder adds the bits x naught, y naught, x input, y input, and the carry input, and produces the output d. So here x input is nothing but a input. Here a bits are given as the x input, so x equals to a. So d is equal to a plus y plus carry input c. So the equation is represented here. As we see these combinations, the first two combination has the select inputs S1 and S0 equal to 0, 0, and the next two combinations has the select inputs S1, S0 equal to 0, 1, and the next two combinations has the select inputs S1, S0 equal to 1, 0, and the last two combinations has the select inputs S1, S0 equal to 1, 1. So when S1, S0 equal to 0, 0, all the 0 inputs of the multiplexers are selected. Here 0 inputs are nothing but the bits of register B. So when S1, S0 equal to 0, 0, B register is selected by the multiplexer and given as the Y inputs to the full adder. So when S1, S0 equal to 0, 0, Y equals to B. And Cin has the two possible values 0 and 1. When Cin equals to 0, then D is equal to A plus Y is nothing but B plus Cin is nothing but 0. So D equals to A plus B, which is nothing but addition operation. When Cin equals to 1, D is equal to A plus Y, B plus Cin 1. So D equals to A plus B plus 1, which is nothing but addition with carry. And when S1 is not equal to 0, 1, all the 1 inputs of the multiplexer are selected. Their 1 inputs are nothing but complements of B. So when S1 is not equal to 0, 1, complements of B are selected by the multiplexer and given as the Y inputs to the full adder. So when S1 is not equal to 0, 1, Y equal to B bar, that is B complement. Then when Cin equal to 0, output D is equal to A plus B bar plus 0, which is nothing but A plus B bar, that is subtract with borrow operation. And when Cin equals to 1, D is equal to A plus B bar plus 1, which is nothing but A plus 2's complement of B, that is subtract operation. And when S1 is not equal to 1, 0, all the two inputs of the multiplexers are selected, which is nothing but logic 0. So when S1 is not equal to 1, 0, logic 0 is selected by the multiplexers and given as the Y inputs to the full adders. So when S1 is not equal to 1, 0, Y is equal to 0. Then output, when carry input Cin equal to 0, output D is equal to A plus Y 0 plus Cin 0. So D equals to A. Here we are transferring the contents of A to the register D. This is nothing but transfer operation. And when Cin equals to 1, then D is equal to A plus 0 plus 1, which is nothing but A plus 1, that is increment operation. And when S1 is not equal to 1, 1, logic 1 is added. All the 3 inputs of the multiplexers are selected. 3 inputs is nothing but logic 1. So when S1 is not equal to 1, 1, logic 1 is selected and given as the inputs to the Y inputs to the full adder. So when S1 is not equal to 1, 1, Y is equal to 1. And when carry input Cin is equal to 0, then D is equal to A minus 1 plus 0. Here A minus 1 because here we are adding logic 1. Logic 1 is nothing but 4 ones, 1, 1, 1, 1. When logic 1 is added to the register A, it should be represented with a negative symbol, that is negative sign. So D is equal to A minus 1. This is nothing but decrement operation. Here we are decrementing the contents of register A by 1. And when Cin equals to 1, then D is equal to A. As we said, Y should be considered with negative sign. So Y equals to minus 1 plus Cin equals to 1. So A minus 1 plus 1, which is nothing but A plus 0. So D equals to A. Here we are again performing the transfer operation. So this is all about the arithmetic circuit, and when we consider n-bit arithmetic circuit, then we should implement n number of full adders and n number of multiplexers, 4 by 1 multiplexers. So this is all about the arithmetic circuit. By this we have completed the topic arithmetic micro operations. Hope I am clear with the lecture. So we have what we have learned in the video is the implementation of arithmetic circuit. So hope I am clear with this lecture, and the next topics will be covered in the upcoming videos. Until then, get subscribed to EduMoon. Thank you and see you all in the next videos.